Good morning, sir.
Yes, good morning. In the previous class, we have discussed that moving charges and magnetism. In that, most important, many times repeated problems based on the cyclotron. Cyclotron is a charged particle which accelerates the charges. Cyclotron is a charged particle that accelerates the charges. So the cyclotron that consists of the two Ds. In between the two Ds, the charged particles, they'll move. Whenever I take, I'm going to correct this. Whenever the charged particle is enter into the Ds, they will move in circular paths. In the moving charges and magnetism, two parts are there. First one is when the charged particle that enters into the Ds, that we call cyclotron imparted based on this. Actually, we don't discuss this in the board exam. For board exam, this part is very less. Cyclotron is a charged, means particle accelerated. It will accelerate both positive and negative charges. This consists of the two D-shaped metal pieces. They are like this. They'll be like this. This is a D-shaped metal. A lower region is connected with an AC source. Is connected to an AC source, oscillated. So this is called a middle portion. A charged particle that is placed here, that will be accelerated and it comes out. So here one exit will be there. Through the exit, it will come out. The charged particle will come out through the exit. Okay. These are called as the Ds, D1 and D2 we will take. Right. When the charged particle that is moving in circular path, in between that is the time period T is equal to, it didn't set properly. You have removed it. I'll show you that how the cyclotron will be there. The same D shapes only will be there. Ds only will be there. A thought to keep them. This is, it will be like this. A charged particle will be there. These are like a D shapes. A charged particle that moves like this, like this, like this, like this, and it will retain. Whenever it is moving, that linear velocity that increases, but angular velocity of the charged particle that remains constant. Like this come out, it will come out. These are D shapes, or another diagram is like this. See, these are also D shaped. Okay, this is a cyclotron. Or in real, for visibility, actual cyclotron will be like this. This is that actual cyclotron. But in our diagram, in our theoretical purpose, we used to say like this. These are the cyclotrons. Like this we'll write. Or we'll say that this is all these are diagrams. Oscillator is connected like here. So after attaining that maximum linear velocity and radius of this charged particle also increases in between that 2Ds. So every time that increases its radius, and finally that comes out. This is the cyclotron. Fine. Then whenever the charged particle is moving, what is the time period? Here magnetic field will be applied around it. Magnetic field is applied. Time period T is equal to 2 pi m divided by BQ. 2 pi m divided by BQ is to say, if it is charged particle of charge, if you take E, then T is equal to 2 pi m into BE also we may write. 2 pi m into BE. Like this also we may write. It's a time period. Frequency. Yeah, 1 pi. Reciprocal of the time period is called as the frequency. Frequency F is equal to 1 by T. Therefore, F is equal to BE divided by 2 pi m. This is the frequency of the charged particle. If you want the velocity of the charged particle, all this. When the charged particle that enters into the in between the Ds, or it enters into the uniform magnetic field. So both electric field may act, only electric field may act based on that. So then centripetal force will be provided by the magnetic force. Whenever the charged particle that enters into the in between the Ds, or into that Ds region, into the cyclotron, force experienced by the magnetic field will provide the centripetal force. Force experienced by the magnetic field provide the centripetal force. Okay, this force experienced by the magnetic field is taken as F is equal to FB is equal to BQ. BQV. Then the centripetal force mv square divided by r for radius. Okay, b get cancelled. Then from this, if you bring these to left side, r, it comes to this side. R is equal to mv divided by bq. Radius of the circular path r is equal to mv divided by bq. Radius of the circular path r is equal to mb divided by bq. R is equal to mb, we can write p divided by bq. mb is equal to p divided by bq. So from that we'll write momentum p is equal to bq into r. Momentum p is equal to bq into r. Like this we will write momentum. Then kinetic energy we can write from it. Kinetic energy of the charged particle, Ke is equal to p square divided by 2m. Kinetic energy Ke is equal to p square divided by 2m. So Ke is equal to p square means what? B square q square r square. See how to write? B square q square r square. B square q square r square divided by 2m. This is the kinetic energy of the particle, charged particle in between the Ds. We may take all of this. So radius we got. Velocity if you want. Velocity of the charged particle if you want. From this we'll write that. Velocity V is equal to BQ into R divided by M. This is the velocity of the charged particle in between the Ds. These are the formulas. Okay, once again, I will write all these formulas, please, because this is the most important part. Problems are there. Most of theory bits they are asking from this cyclotron. First one, velocity of the charged particle. V is equal to B Q R divided by M. This is the velocity of the charged particle. Second one, radius we got is radius of the charged particle. It is equal to R is equal to MV divided by BQ. MV divided by BQ. Third one, momentum of the charged particle. P is equal to BQ into R. Next, kinetic energy. KE is equal to KE, we got B square Q square, B square Q square R square divided by 2M. Next, time period. T is equal to 2 pi M divided by BQ. The next one is the frequency. BQ divided by 2 pi M. 2 pi M. Please go through these once. Right, these are the charged particles. Fine, I am going to solve the numericals. These are previous 2020, 19, 18 in CET exam they have given. A cyclotron is used to accelerate protons, deuteriums, and alpha particles while existing under the similar conditions. The minimum kinetic energy. So then kinetic energy expression just have explained, I have written kinetic energy of this charged particle. Kinetic energy. Kinetic energy of the charged particle just have written. Ke is equal to B square Q square, B square Q square, R square divided by 2M. There, kinetic energy that depends upon the square of the charge and mass. This value, whenever we write, charge of the proton is taken as, for proton, charge is taken as E, and for deuterium, charge will be taken as E only, and alpha particle charge is 2 times the charge of the proton. Next, mass, whenever we consider, mass of the proton is taken as M, MP only. So mass of the deuterium is equal to 2 times the mass of the proton, and mass of the alpha particle is 4 times the mass of the proton. So this Q square by M value will be less for deuterium. Q square divided by M is less for deuterium. Q square divided by is mass, this 2M is there and charge is there. But here mass 4M is there, but charge 2 whole square is there. That's why minimum Q square divided by 2M is a minimum for deuterium. That's why this kinetic energy is minimum for deuterium. Kinetic energy is minimum for deuterium. The option is correct. So if you want, you may check that all the conditions. for proton, deuterium, and alpha particles. Q square divided by m will be minimum for deuterium. Next problem. In a cyclotron, a charged particle speeds up in D's. Speeds up between the D's because of the magnetic field. In a cyclotron, a charged particle that accelerates, because continuously it moves from the one D to other D. So it undergoes acceleration all the times. In a cyclotron, a charged particle, it won't be at rest. It will circulate with the high speed that comes out, right? So it undergoes acceleration at all time, means always. It undergoes acceleration always. Next, a cyclotron is used to accelerate both positively charged and negatively charged particles. A cyclotron is used to accelerate both positively charged and negatively charged particles. Both positively charged and negatively charged particles. Next, in a cyclotron, as radius of the circular path of the charged particle increases. So in a cyclotron, as radius of the charged particle, circular path of the charged particle increases, linear velocity increases, but angular velocity remains constant. Linear velocity that increases and angular velocity remains constant. Then a proton is projected with uniform velocity along the axis of a current carrying solenoid. Then a proton is projected with uniform velocity v, here it is v, along the axis of a current carrying solenoid. A proton is projected with uniform velocity v along the axis of a current carrying solenoid. Then for this we'll take proton will continue with the velocity v along the axis. So a proton is projected. What did they ask? What did they say? A proton is projected with uniform velocity v along the axis of a current carrying solenoid. Then the proton will continue to move with velocity v along the axis. The proton will continue to move with velocity v along the axis. Next, if a velocity has both perpendicular and parallel components while moving through a magnetic field. If a velocity has both perpendicular and parallel components while moving through a magnetic field, what is the path followed by the charged particle? So it will follow that helical path. So whenever it is there perpendicular field, it moves circular path. And whenever it is the parallel field is there, it will move in linear path. So whenever it is there perpendicular, due to perpendicular component, will say that charged particle that will get circular path, and due to parallel field it move linearly. So due to that helical path, it will move, helical path is correct. Next, a charged particle experiences magnetic force in the presence of the magnetic field. Which of the following statement is correct? A charged particle experiences magnetic force in the presence of magnetic field. Which of the following statement is correct? A charged particle experiences a magnetic force in the presence of the magnetic field. Which of the following statement is correct? Which of the following statement is correct? A charged particle experiences magnetic force in the presence of magnetic field. Which of the following statement is correct? So then particle is stationary magnetic field, particle moving and particle is moving and magnetic field is perpendicular to the velocity. Yes. A charged particle experiences magnetic force in the presence of magnetic field. Which of the following statement is correct? They have asked it. So a charged particle, the charged particle is moving and magnetic field is perpendicular to the velocity. The charged particle is moving and magnetic field is perpendicular to the velocity. This. A circular coil of radius 10 centimeters and 100 turns carries current of 1 ampere. What is the magnetic moment? Magnetic moment of this solenoid or magnetic moment of this circular coil carrying current M is equal to NIA. A for area of cross section. M is equal to NI into pi r square. We'll see what is the given data. Radius r is given as 10 centimeters. Then r is equal to 10 into 10 power minus 2. That will be r is equal to 10 power minus 1 meter. Their number of turns, n is taken as 100. N is taken as a current. I is equal to 1 ampere. I is equal to 1 ampere. Then M is equal to, N means number of turns. Number of turns are taken as 100. 100, 1 ampere into pi. Pi value 3.142 into R. R is the radius. What is the radius? 10 power minus 1 whole square means what? 10 power minus 1 whole square. It becomes 10 power minus 2. See, this 10 power minus 2 and 100 will get cancelled. What is there? The magnetic moment M is equal to 1 into 3.142. It will be 3.142. 3.142 ampere meter square. 3.142 ampere meter square. This is 3.142 ampere meter square. Right. Next problem. A proton beam enters into a magnetic field of 10 power 4 Weber meter normally. If the specific charge of the proton is this is 10 power minus 4, the data, its mistake is there. It is 10 power minus 4, 10 power 11, 10 power 11 B, so velocity V is 10 power plus 9. This is the data. It's a printing mistake. A proton beam enters a magnetic field of 10 power minus 4 Weber meter normally. If the specific charge of the proton is 10 power 11 Coulomb per kc and its velocity is 10 power 9 meters per second, then the radius of the circular path is For us, what is given? Magnetic field means magnetic induction. B is equal to 10 power minus 4 Weber per meter square. It is Weber per meter square. That is also printing mistake. So Weber per meter square. The specific charge of the proton is E by M. E by M is given as 10 power 11 Coulomb per kg, 10 power 11 Coulomb per kg, and its velocity is velocity V is equal to 10 power 9 meters per second. This is so. Then the radius of the circular path is, what is the radius of the circular path that we have to take? Just to have explained you radius of the circular path, R is equal to mv divided by be. R is equal to mv divided by be. Proton, they told, proton means proton mass, we have to take it. So it is given that directly velocity is given. Then instead of this, we will write this to denominator. Specific charge you have to write. That's why this R modifying this formula. How to write it? R is equal to m into V divided by E into B, we will write. This is there. If I bring this m to denominator, it will be like this. R is equal to V divided by E by m into B. R is equal to V divided by E by m into B. Therefore, R is equal to, what is the velocity? 10 power 9. What is the specific charge? E by m, it is given. E by m, it is given as 10 power 11. See, E by m is 10 power 11 into, what is the magnetic field? B. B is equal to 10 power minus 4. This will be R is equal to 10 power plus 9 in the numerator, and in the denominator 10 power 7. If it comes to numerator, R is equal to 10 power plus 9 into 10 power minus 7. There R is equal to 10 power plus 2. R is equal to 10 power plus 2. R is equal to 10 power plus 2, nothing but 200. R will be equal to 100. Please go through it. If we didn't get, I'm ready to repeat this problem. Next. Conversion of the galvanometer into ammeter as well as voltmeter. A galvanometer can be converted into ammeter by connecting a suitable low resistance in parallel to each. That is, suitable low resistance whenever it's connected parallel to each. Conversion of galvanometer. Conversion of galvanometer. Conversion of galvanometer into ammeter. Conversion of galvanometer into ammeter. A galvanometer can be converted into ammeter by connecting a suitable low resistance in parallel to it. Let us suppose it is the galvanometer. For this galvanometer, a suitable low resistance should be connected in parallel to it. This is taken as a galvanometer. For this galvanometer G, low resistance should be connected parallel to it, that we call. This is a low resistance, we used to call it as S. S is the low resistance connected. Then the total current that is entering is taken as I. I splits at this point. I splits as Ig, that is passing through the galvanometer, and I minus Ig, that is passing through the low resistance. So this is that conversion part of the galvanometer. This is that conversion part of the galvanometer. A galvanometer can be converted into ammeter by connecting a suitable low resistance to it. It is called as the it's called low resistance connected to it. The low resistance is taken as S. Okay. Then current passing through that low resistance we can calculate. Current passing through the galvanometer we may write. What is the formula to calculate current passing through the galvanometer? So Ig for galvanometer current, Ig is equal to I into S divided by G plus S. I into S divided by G plus S. Ig is equal to I into S divided by G plus S. What is the current that is passing through the low resistance? Is equal to I into G divided by G plus S. I into G divided by G plus S. This is the formula to calculate that low resistance, means current passing through the low resistance, right? So whenever we take number of turns, N is taken as and we'll take that current, total current to that current passing through the galvanometer. N is equal to I by Ig. N is equal to I by Ig. So there, the relation between these are low resistance, how much it is connected if you want. S is equal to G divided by I by Ig minus 1, or the formula is S is equal to G divided by N minus 1. Low resistance S is equal to G divided by N minus 1. These formulas are most important. This is important. Based on this, from many years onwards, they are asking problems. All type of either APMT, CET, NEET, mains, based on these problems will be there. S is equal to G divided by N minus 1. What is N? I by Ig. What is I? Total current. What is G? Current passing through the galvanometer. Right? So S is equal to G divided by N minus 1. S is equal to G divided by N minus 1. This is. Or if you want to convert this galvanometer into voltmeter, to convert the galvanometer into voltmeter, conversion of galvanometer into voltmeter. Conversion of galvanometer into voltmeter. So this is a galvanometer. Galvanometer it is. For this, if you want to convert this galvanometer into voltmeter, a low suitable resistance should be connected. High resistance is to be connected. Low not. High resistance is to be connected. High resistance is to be connected. High resistance is to be connected. This is the current, the galvanometer. This is the resistance R. conversion part is taken like this. This is conversion part. I is equal to Ig. In series combination, same current passes. That's why I is equal to Ig. Then low resistance is taken as means high resistance is taken as R. R is the high resistance that is to be connected. Conversion part of the galvanometer into voltmeter. So then V is equal to Ig into capital G plus R. Ig is equal to V is equal to Ig into capital G plus R. Because total resistance in series combination is R is equal to RS is equal to R1 plus R2. G and R, they are in parallel. So we'll write that V is equal to Ig into G plus R. Ig into G plus R. Therefore, we will take that V is equal to Ig into G plus R. Therefore, we will take N is taken as total potential difference across the galvanometer is taken as Vg. Vg is the potential difference across the galvanometer, V suffix G. And total potential it is connected is taken as V. Then V by Vg, that gives that N. N is the ratio of the total potential to potential difference across the galvanometer. So the total potential ratio of total potential to potential across the galvanometer is taken as N. N is equal to V by Vg. Therefore, we'll write that the resistance is to be connected. First, if I want R value, we have to bring this Ig to left side, G to left side, like that we'll write it. Okay, so afterwards we'll calculate what is the high resistance that should be connected. High resistance should be connected will be equal to V by Ig minus capital G. How much high resistance is to be connected? V by Ig minus capital G. This is the resistance that is should be connected. R is equal to V by Ig minus capital G. This is the resistance that is to be connected. So therefore, R is equal to capital G into N minus 1. Capital G into N minus 1. Why? How to write this? We'll write this. Ig is equal to then we'll write R is equal to G into N minus 1. Okay. Then one problem will solve based on this. Once again, I'll write this. What I have explained. If you want to convert galvanometer into voltmeter, high resistance is to be connected. High resistance R is equal to V by Ig minus capital G. This is the formula to calculate high resistance. Otherwise, N is that ratio of the total potential to potential difference across the galvanometer. So resistance R is equal to capital G. High resistance is to be connected. R is equal to capital G into N minus 1. Otherwise, that will write G into V by Vg minus 1. V by Vg minus 1, that we will take. R is equal to G into V by Vg minus 1, that we will take. R is equal to G into V by Vg minus 1, it is. Right? Then R is equal to G into N minus 1 also we may write. This is. So that if it is for the conversion of the galvanometer into ammeter, in such case, low resistance should be corrected. S is equal to G divided by I by Ig minus 1. These formulas also important. Based on these problems they are asking. S is equal to G divided by N minus 1. S is equal to G divided by N minus 1. S is equal to G divided by N minus 1. This is the formula. Right. See, it is given. A galvanometer resistance is 50 ohms, gives a full scale deflection for a current of 5 into 10 power minus 4 amperes. The resistance that should be connected in series with a galvanometer to read 3 volts. It has to read what is the voltage 3 volts. Galvanometer resistance is given. Means internal resistance of the galvanometer is given. It is taken as 50 volts. Then full scale deflection means what? Current passing through the galvanometer. Ig is equal to 5 into 10 power minus 4 amperes. The resistance that should be connected in series means what? Low resistance means series means high resistance. High resistance. How much high resistance should be connected? High resistance should be connected with a galvanometer to read the 3 volts. It has to read the voltage, how much? 3 volts. V is equal to 3 volts. Then what is that resistance is to be connected? I told you that V is equal to Ig into capital G plus R. This is the formula. From this formula, I want what is the R? R is equal to V by Ig minus capital G. This is the formula to calculate the resistance. What is the formula? V is equal to, R is equal to V by Ig minus G. V by Ig minus G. Therefore, R is equal to, V is how much? V is equal to 3 divided by Ig how much? 5 into 10 power plus 4. 5 into 10 power plus 4. I'll write neat. Ig is equal to 5 into 10 power minus 4, sorry, minus G. What is the capital G value they give? 50. Then R is equal to this 10 power plus 4 if it comes to numerator. It is 3 into 4 zeros. 1, 2, 3, 4 zeros divided by 5 minus 50. See, this will get cancelled 6 times. So 6 into 000, 6,000 it is. 6,000 minus 50. This is what? 50. 6,000 minus 50 will be equal to, therefore R is equal to 5,950. B option is correct. 5,950. B option is correct. Okay. I am going to that next chapter, electrostatics, as to say. Both electric fields and charges and electric potential and capacitance, as to say, it is electrostatics. 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 In the electrostatics, we will take that charges. charge Q is equal to N into E. We will write Q is equal to N into E. How many electrons will be there in 1 coulomb of the charge? So charge, it is measured in coulombs. So coulomb is the unit of the charge. Charge Q is equal to N into E. Then charge unit of the charge is Coulomb. It is a larger unit. Small units of the charge are microcoulomb. 1 microcoulomb is equal to 10 power minus 6 coulombs. 1 nanocoulomb. 1 nanocoulomb is equal to 10 power minus 9. 1 picocoulomb. 1 picocoulomb is equal to 10 power minus 12 coulombs. This is so like this. We may write this the units of the charge. Quantization of the charge, it is Q is equal to N into E. So they may ask how many electrons are there in 1 coulomb of the charge. How many electrons are there in 1 coulomb charge? How many electrons are there in 1 coulomb charge? So 1 coulomb charge, Q is given as 1 coulomb. Charge of the electron E is taken as 1.6 into 10 power minus 19 coulombs. According to quantization of the charge, Q is equal to N into E. Therefore, N is equal to Q divided by E. N is equal to Q divided by E. Then N is equal to, what is Q? Q is 1. Q is 1 divided by E is 1.6 into 10 power minus 19. 1.6 into 10 power minus 19. See, 1 by 1.6 will be equal to 0.625. 1 by 1.6 will be 0.625 into 10 power plus 19. This generally we used to write N is equal to 6.25 into 10 power 18. This, how many electrons are there? 6.25 into 10 power 18 electrons will be there. In 1 coulomb of charge, these many electrons will be there. So we have to split the charge into 2 parts. First of all, we have to go for Coulomb's law. Coulomb's law, called as Coulomb's inverse square law. When the 2 charges are separated by distance, Q1 and Q2 are the 2 charges. Q1, Q2 are the 2 charges which are separated by a distance R. According to Coulomb's inverse square law, when the two charges Q1 and Q2 when the 2 charges Q1 and Q2, they are separated by a distance R. Q1, Q2, if they are separated by distance R, then force is directly proportional to charges Q1 and Q2. Force is directly proportional to Q1 and Q2. F is equal to, and is inversely proportional to, F is inversely proportional to R. Inversely proportional to R square. Combinedly, we'll write that F is proportional to Q1, Q2 divided by R square. What is this? F is equal to 1 by 4 pi epsilon naught into 1 by 4 pi epsilon naught into Q1, Q2 divided by R square. Where 1 by 4 pi epsilon naught is a constant. 1 by 4 pi epsilon naught is equal to 9 into 10 power 9. Newton meter square per Coulomb square. What is mu epsilon naught? Epsilon naught is called as the permittivity of free space. Permittivity of free space that we will take. It's called as the permittivity of the free space we will take. Epsilon naught is the permittivity of the free space. What is the value of epsilon naught? Epsilon naught will be equal to 8.85 into 10 power minus 12 farad per meter. 8.85 value, 8.85 in 10 power minus 12 farad per meter. See, this force depends upon the product of the charges. Force between the charges depends upon the product of the charges. Force depends upon the product of the charges. So whenever we take that, a charge Q is to be split. A charge Q is there. A charge Q should split into two parts. A charge Q is there. Capital Q is there. That we have to split into two parts. We have to split into two parts. The parts they are taken as Q1 and Q2. We have to split the charge capital Q into two parts. That means capital Q should be equal to Q1 plus Q2. Then how these charges will be there to get the maximum force and to get the minimum force between them. To get the maximum force between them, we have to split these charges as to get the maximum force between them. Maximum force between them. How to split it? Q1 is equal to capital Q divided by 2, and Q2 is equal to capital Q divided by 2. To get the maximum force, we have to split. Q1 is equal to Q by 2, and Q2 also equal to Q divided by 2. Q1 is equal to Q by 2, Q2 is also Q by 2. So then how these are? Q to get the minimum force. To get the minimum force. To get the minimum force, the charges. Q1 is equal to 1 Coulomb and Q2 is equal to Q minus 1 Coulomb. Q minus 1. This, we have to split like this. Maximum force and minimum force. If you take the ratio of maximum force to minimum force, F maximum divided by F minimum, to get the maximum force minimum force ratio. Q square divided by 4 into Q minus 1. These are that charges. F maximum, F minimum is equal to Q square divided by 4 into Q minus 1 we will take. Right? Then whenever we take this gravitational force, electromagnetic force, and strong nuclear force, weak nuclear force. So then force between the electrostatic force. Electrostatic force is 10 power 36 times greater than that of the gravitational force. And the strong nuclear force strong nuclear force is about 10 power 38 to 10 power 42 times greater than the gravitational force. 10 power 38 to 10 power 42 times greater than the gravitational force, right? That we will take. Okay, so then two charges are there. Two charges are separated by certain distance. They are maybe like charges or maybe unlike charges. So two charges, they are taken as a Q1 and a Q2. They are separated. So then if they are like charges, if they are the like charges, the neutral point will be formed between the charges. This Q1, Q2 are taken as the two like charges. The neutral point for the like charges will write location of neutral point, location of the neutral point for like charges. For like charges. For like charges, this neutral point will be formed between the charges. Neutral point will be formed between the charges. Let us suppose these are the two charges. These are the two charges Q1, Q2. So the location of the neutral point is, this is a neutral point here, which is at a distance x from the first charge. These are separated by distance r. R is the separation between the charges. The position of the neutral charge is at x from the first charge. This will be r minus x. Then distance of the neutral point from the smaller charge is x. Here we have take Q1, Q2, Q2 is greater than Q1. We have to take Q2 is greater than Q1. So x is equal to let us suppose r is the distance between them. R divided by square root of Q2 by Q1 plus 1. This is x is equal to r divided by square root of Q2 by Q1 plus 1. This is the distance of the position of the neutral, distance of the location of the neutral point from distance. It is the location of the neutral point from the weaker charge. Q2 is greater than Q1 means Q1 is weaker than that of Q2. This is the like charges. Okay. For unlike charges, if unlike charges are taken, for unlike charges, position of the neutral point is outside. Location of the neutral point is at a distance of y. Separation between them is taken as a d. This is the distance y. This is the position of the neutral point. Here also for unlike charges. Here also Q2 is greater than Q1 we used to take. Q2 is greater than Q1. Therefore, position of the neutral point from the weaker charge, y is equal to r divided by square root of Q2 divided by Q1 minus 1. Q2 by Q1 minus 1. It is. Right. So then we go for electric field intensity or intensity of the electric field. Electric field intensity or intensity of the electric field. So this intensity of the electric field is located intensity of the electric field is nothing but force experienced per unit charge. Force experienced per unit charge is called as the intensity of the electric field or electric field intensity. Electric field intensity is equal to F divided by Q. Electric field intensity is equal to F divided by Q. This is the expression for the intensity of the electric field. This is the expression for intensity of the electric field. F is equal to Q. Its unit is taken as unit of the electric field intensity is Newton per Coulomb. Its unit is taken as Newton per Coulomb. Newton per Coulomb or intensity of electric field N Newton per Coulomb, Newton per Coulomb or volt per meter. This electric field intensity, it is away from the positive charge. Electric field intensity is away from the positive charge, or electric field intensity, direction of the electric field intensity is towards the negative charge. Direction of the electric field intensity E bar is like this. So electric field intensity away from the positive charge, it is directed towards that negative charge. Direction of the electric field intensity will be like this, that we will take. So then we calculate the electric field intensity at a point. Electric dipole. Electric dipole. So when the two charges are separated by certain distance, two charges are minus q and plus q. When the two charges minus q and plus q, which are separated by a small distance, forms an electric dipole. When the two charges q minus q and plus q, they are separated by small distance. This is called as the electric dipole. Two charges minus q and plus q, they are separated. It's called it forms an electric dipole. A straight line that is passing through the two charges we call axial line. A straight line that is passing through the two charges is called axial line. A straight line which is perpendicular to that axial line and passing through the center of the dipole is called as the equatorial line. Equatorial line it is. Axial line and equatorial line. These are the electric means we can calculate the electric field intensity at a point on the axial line and at a point on the equatorial line. Electric field intensity at a point on the electric field intensity at a point on the axial line. 1 by 4 pi epsilon naught into 1 by 4 pi epsilon naught into 2pr divided by r square plus r square minus a square, r square minus a square whole square it will be there. For the far field, we'll write that EA is equal to 1 by 4 pi epsilon naught into 2p divided by r cube. This is at a point on the axial line. Then electric field intensity at a point on the equatorial line. Electric field intensity at a point on the equatorial line is equal to 1 by 4 pi epsilon naught into P divided by R square plus X square, R square plus A square whole power 3 by 2. R square plus A square whole square is 3 by 2. R square plus A square whole square it is. R square plus A square whole square. Let me check it. R square plus A square whole square. R square plus A square whole square it will be there. One moment. One moment. I'll come now only. Electric field intensity at a point on the equatorial line. At a point on the equatorial line, we have to see that electric field intensity at a point on the equatorial line. So 1 by 4 pi epsilon naught into P by R square plus A square whole power 3 by 2. 3 by 2 is correct, right? So E equatorial is equal to 1 by 4 pi epsilon naught into P divided by R square plus A square whole power 3 by 2. This is at equatorial line. It is at the equatorial line. For the far field, and then E equatorial is equal to 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. P divided by R cube. P divided by R cube. Okay. Then Gas law. Gas line electrostatics. Gas line. The total electric flux through any closed surface is the total electric flux through any closed surface is equals to 1 by epsilon naught times the 1 by epsilon naught times the the net charge enclosed times the net charge enclosed. 1 by epsilon naught times the net charge enclosed. So the total electric flux through any closed surface is equal to 1 by epsilon naught times the net charge enclosed by the surface. Net charge enclosed. So according to electric flux, the total electric flux phi is equal to 1 by epsilon naught times the net charge enclosed. This is taken. It is. For example, there is a closed region. There is a closed region. These are the charges. Q1, Q2, Q4, and Q5, like that. Q6 minus Q. This is a plus. Q3, right? This is taken as a Q1 minus Q2 plus Q3 plus Q4 and Q6 like this. The total flux phi is equal to 1 by epsilon naught times the net charge enclosed. So net charge enclosed will be equal to Q1 plus Q1 minus Q2, Q1 minus Q2 plus Q3 plus Q4. Q1 minus Q2 plus Q3 plus Q4. This will say Q is equal to 1 by epsilon naught times that Q1 minus Q2 plus Q3 plus Q4. This is the net charge enclosed. Right? This Q6 is not, Q6 is there. This is not included. It is not inside that closed surface. That's why we'll say that. That's why we will say that flux is not included. Right? Flux is not included. Let us suppose a closed one is there. Whatever it may be the shape. If a closed region, whenever we consider, in the closed region, a charge Q is placed. What is that net flux through each? Flux phi is equal to 1 by epsilon naught times the charge enclosed. For example, instead of this, I used to take a charge is placed in a closed region. It is a closed region. In the closed region, charge Q1 and Q2 they have placed. What is the net flux through each? Flux phi is equal to 1 by epsilon naught into Q1 plus Q2 we will take. Instead of that, it is enclosed by the dipoles. What are that? Minus Q and plus Q. It is one electric dipole. This is one electric dipole. Like many dipoles, they might be there. Minus Q and plus Q. They'll be there. So like dipoles, if they are, flux phi is equal to 1 by epsilon naught times that net close and net charge enclosed. Net charge enclosed. So in this, if we keep that dipoles, what is the net charge? Net charge will be equal to 0. If the dipoles, n dipoles if they have placed, 1 dipole, 2 dipole, 3 dipoles, whatever it may be. So positive charge or negative charge, they'll get cancelled. The flux due to the positive charge, flux due to the negative charge, that cancel. That's why we'll get only the net charge is taken as 0, flux phi is taken as 0. As the net charge is taken as a 0, flux through this surface also will be equal to 0. That we will take. So let us suppose a charge is placed in a closed region, whatever it may be that closed region it is. Let us suppose it's a closed region. In this closed region is to keep a charge Q. The net flux phi is equal to 1 by epsilon naught times the 1 by epsilon naught times that net charge enclosed. If I take a closed region like this, if I keep a charge Q here, if I keep the charge Q, the flux phi is equal to 1 by epsilon naught times the charge enclosed. If the flux phi is equal to 1 by epsilon naught times the charge enclosed by it. Like that we will take. So this is, if a charge Q is there at the center of the cube, the flux through the total flux is, this is called as the total flux. Total flux is equal to 1 by epsilon naught times the charge enclosed. Next, the flux through phase. So how many phases will be there? 6 phases will be there. So flux through the phase will be equal to 1 by 6 epsilon naught, 1 by 6 epsilon naught into Q. So flux through that coordinates. So how many coordinates will be there? So 8 coordinates will be there. Flux through that coordinates, 8 coordinates will be there. 1 by 8 epsilon naught into Q. So then flux through that edge. How many edges are there? 12 edges will be there. 1 by 12 epsilon naught into Q. This is a flux through any closed surface. Okay, I'm going to stop the class here. We'll see the next class in the tomorrow, and day after tomorrow I'm going to complete that syllabus. Please attend tomorrow and day after tomorrow also. Right, thank you.